Hi, I'm Matthew at Northeastern University. I'm going to be presenting my talk, Manipulating Machine Learning, Poisoning Attacks, and Countermeasures Against Regression Learning. This is joint work with my advisors, Christina Nita Rotaru and Alina Oprea, both at Northeastern, Batista Bijo at University of Cagliari, and Cheng Liu and Bo Li, both at UC Berkeley. So, you can see supervised machine learning is a pretty common task these days. Basically how it works is you start with a training data set with data and labels. You feed this into the next slide. So you feed this into a learning algorithm and it produces a model. And the point of this model is the next slide, where you use it on new data that it hasn't seen before and it produces new labels. Great. So I don't know, am I not pressing it hard enough? So there are two kinds of prediction tasks you might consider in supervised machine learning. The first is classification. Can we go to the next slide? Am I not pressing it hard enough? Okay, so the first is classification, where you know that you have a discrete output space, and so you're going to be predicting a class corresponding to your given input. And this is something, this is common in the security community. You can think like malware classification or the like. And then, and then you also have regression, where you know that you have a continuous output space, and so you're going to be predicting this response value given in input data. And I'm sorry, but this is, can we go back like 3, 4 slides? So there's classification and regression. This one is, so classification and regression. This is, I guess, a visual, but I already told you about it. So I guess the next slide. Can we go back one? All right, so now what's a poisoning attack? So an adversary is able to add points at training time, and this is going to, the learning algorithm is going to incorporate these points into the model that it builds at, and then the model is going to be incorrect at test time because it's using this incorrect training data. So in this talk, we're going to be talking about regression models. So we're going to focus on Ridge for this talk, but we test against other ones in our paper. I'm going to be telling you about our poisoning attacks that we developed called OptP and StatP, and then our defense TRIM, and a bit about evaluation. Great. So, so linear regression is a type of regression model. So you have data and your response values. And you can, and you want to build a linear model in order to predict the response values from the given data. So you can see this on the right. These red dots have the X values. This is the data, the features. And the response values are the Y values. And our goal is to build this blue line that cuts through them. And the way you do this is by minimizing a loss function over your training data. This consists of two parts. You have the regularization, or sorry, you have the residuals piece, which is basically how well your model fits your training data. This is also called mean squared error. And then you have your regularization piece, which prevents overfitting. All right, so what is a poisoning attack? It's this thing here, and I hope this doesn't solve any problems for you in your head. So let me unpack it. So basically, you start with a training data set. And your adversary is going to be able to add poison data points into your training data set. And the way they're going to do this is in order to maximize their objective. So this might be the training loss or something like that. And the thing is, the objective, they only have control over this corrupted model. And it's learned by minimizing this loss function over both the training and the poison test data. And this is actually very hard because you only have control, your adversary only has implicit control over their objective based on the entire training process. And so this turns into a bi-level optimization problem, which is NP hard in the general case. So in order to approach this, we're going to define our adversary. We consider two adversaries, a white box and a black box attacks. We have white box attacks where the adversary knows everything. This is the training data, hyperparameters, the algorithm that's being used. And then we also have a black box attack where they only are allowed query access to the model and statistical information. And then we also have some parameters that our adversary is going to satisfy. They are only able to add some alpha fraction to the data set. And then the values for the points they can add are going to be bounded within the natural bounds of the feature. And this is what we're going to be determining from the training data. And the goal of our adversary is just going to be indiscriminate availability, which just means we're going to maximize the loss of the model. Great. So how do we do this? We're going to use, first, optimization-based poisoning attacks. So we start with a set of good initial poisoning points, and we want to run gradient descent on these points. And gradient descent is just a greedy optimization approach. What you do is you start with a point, and you see which direction is going to improve my point the most, and you keep doing that until you're satisfied with where you're at. You can see this on the right. These points are starting in like these little blue valleys. They're taking steps upwards, and they're getting into the red area. Great. So people have done this in the past for this kind of attack. On the next slide. So people have done this in the past for these kinds of models for classification setting. And their objective was to maximize the regularized training loss. The way they initialized their points was just by flipping over the model. And they ran gradient descent in order to optimize their x value. The gradient looks like this, which is it's just some linear algebra once you know the gradient of the model parameters with respect to the point that you're adding. This is a very non-trivial dependence because it's the output of this optimization process again. And so what they did was they used the KKT conditions for this model in order to drive a linear equation that they can then solve and compute this gradient. This was at ICML 2015. And what we did is we took this and we saw that there are many ways that you can be improving this attack. First, we know we have a regression task, and so we can also optimize on the y value. And so this actually ends up being just one more linear equation that we need to solve. And you can see this on the right. The y value is this vertical axis. You see that these points are improving a lot when you're able to optimize over the y value. Second, what they did in their work was called inflip, where they just pushed to the other side of the plane. You can see that if you're already close to the plane at the start if you have a good regression model. Flipping isn't going to move you very far, and so we're just going to push it even further. And then finally, we also tested with another loss function. They used the regularized training loss, which is exactly what the learner is trying to minimize. We used a validation set loss. All right, so this actually requires a lot of knowledge about the system, right? The training data, the parameters, and everything. What if their adversary doesn't have access to this? So we also looked at this setting. And we have a black box attack that we call StatP. And all this requires is you're able to sample from the mean and covariance of the training data and then query the model. So how you're going to do this is you sample, you query the model, and then you flip the output using the B-flip that I just talked about. And this is going to be your poisoning point. So this is going to be pretty fast. And basically, you can see kind of some math for why this works. Down at the bottom, the left is your unpoisoned model, and the right is going to be the poisoned model. Basically, this is keeping the statistical properties of the data set pretty fixed while maximizing the modification of the correlations. And so you're going to be poisoning the model pretty effectively. All right, so told you about attacks. How are we going to get around these? So there are people that have, so like what you would want from a defense is you want to identify and train without these poison points. People have built techniques for this in the past. Some were not specifically designed for poisoning, and some were. So some that weren't were Huber loss, modifies the loss function in order to incorporate, or in order to work for larger errors. But this is still going to incorporate these poison points into the model. And so it's not going to be great for an adversarial setting. Then there's also ransack, which samples points and trains on the smaller sample. But this smaller sample is still going to contain poisoning points in a high poison rate scenario. And so it's not going to be great in that setting. And then some techniques were designed for poisoning. Chen et al. Proposed one based on robust dot products, but unfortunately it has strong assumptions about the training data that we don't see satisfied in the data sets we tested against. And then finally, we have RONI, which is a technique from the security community, where you train with and without each training point and evaluate the change in the loss. But unfortunately, this change in loss is evaluated on a model that is poisoned itself, and so it's not going to be great in a high poisoning rate scenario. All right, so these all have their drawbacks. How do we approach the problem? So basically, what you would want for a defense is you want to find the best points and train on them. So if you already know your model parameters, it's pretty easy to find the best points. You just pick the ones with the smallest residuals. But unfortunately, if you're building your model, you don't know the model parameters. And you don't know the true training data distribution either. So the idea is we're just going to alternately estimate these model parameters and find these little residual points. And you can see this working on the right. And you can see at the start, we've got these poisoning points that are pretty significantly altering our model. But after we go through a couple iterations, you can see the line is starting to really match what the true training data is like. Great, so talk to you about attacks, defenses, and I'll talk to you a bit about how we evaluated. I'm not going to get too much into it. We have a lot of experiments in our paper, but for example, we tested on a loan interest rate prediction data set from Kaggle, and we essentially are seeing that both of our attacks are improving pretty significantly over prior work. On the bottom left is the 0% poisoning rate. This is like your ground truth model if you didn't have any poisoning. And we're able to improve upon the existing work by a factor of about like 6.83 in some cases. And we also wanted to evaluate our attacks if we didn't have full training set knowledge. So this is like a transferability attack. So basically, we're able to see that our attacks are pretty transferable even if you don't know the full training data when you're running your optimization. And then, so for our defense, you can see here, this is the same data set. This no defense is right there at the top. Again, the bottom left is an unpoisoned data set. And basically what you would want from a defense is that it's a flat line at the bottom. It's not being affected by poisoning very much. And you actually see this from our defense trim. Other methods, some of them do fairly well, but they're all somewhere in between no defense and this like our defense. So in fact, over all the experiments we ran, we saw that trim was within like 1% of the original model's MSE. All right, so I've talked to you about poisoning attacks on regression models. We're the first to consider regression tasks in the poisoning literature. And then we have two attacks, a white box attack based on gradient descent that we call opt-p, and a black box attack that we call stat-p based on statistics. Basically, opt-p is slower, and it takes on the order of minutes, and then stat-p is faster. It takes seconds or even less than that. And we also made a defense called a trim that's able to mitigate our attacks, and it runs also very quickly. And you can check out our paper for more results and some theoretical analysis. And you can see our code online at this link here. Thank you very much. I'm happy to take questions.
Right, we have time for a few questions. So first of all, I'd like to start with one question. This is very interesting. To me, at least. I'm curious. You work on indiscriminate poisoning, right? So, but there's also, possible sort of attacker goal, which is to do targeted poisoning. So the goal is not to destroy the classifier accuracy, but to affect a specific target, right? So I was curious, what do you think, in the context of these targeted poisoning attacks, would your defense based on minimizing residual or finding looking at the residual loss, would that be a good direction to look for a defense against target poisoning attacks?
I don't think so, because these are typically like you add a small number of points and it's supposed to modify a small number of predictions. I think this is really more for like an indiscriminate case.
Hi, thanks for the talk. I'm curious if your attacks allow you to specify that you want to find a lot of poison points that are really close to the decision boundary, and if so, how that would sort of influence your defense, or do you have other defensive ideas?
Yeah, so something nice about like a gradient-based optimization attack is that you can also add like constraints into the like the optimization or your optimization function that you're using. So yeah, you could definitely also do like projection or stuff to make it so your poison points aren't as far away from the decision boundary.
Gershon from University of Chicago, very nice talk. So I'm wondering, like, it seems like the purpose of defense is to lower the attack's success rate or like the performance. So I'm wondering, like, can you like actually detect the points in the attack before you actually apply your methodology? So for example, given a model or potentially some data set, can you actually tell if the model is poisoned or not?
So I guess in theory you could run like with several different. So like basically you specify how many poison points you think there are. You could run with several different values and see how well it does at all of those values, and see where like if it works at a low value, maybe it's not poisoned very much, and so you can see that.
Okay, thanks.
Yeah.
I was curious about the transferability results, so you went very quickly over them,
Yeah.
because of timing constraints. Can you say a little bit more about because, yeah.
Yeah, so basically the experiment was, we run our attack with full knowledge of the training set. Basically, like I split up the data set into a bunch of different pieces, and I ran the attack on this one. I took these poisoning points and I moved them over to another one. And kind of what we saw was, in some cases, like this was actually even doing better, and so maybe it's like sort of overfitting to the original.
Right, I was wondering if you have any conclusions about, what's likely to transfer, like what types of models or what types of
I mean, so we like tested against regression. I think regression is like pretty likely that it's going to be transferring pretty well.
type of regression.
Yeah.
All right, cool. Let's thanks to the speaker.